Hi, geology students. We're going to start chapter 16. So this is chapter 16, part 1. You can see the chapter outline in front of you. This first video, I plan to cover the first 3 things in the list. And let's take a quick look before we get started at the excerpt of chapter 16 from the final exam study guide. We are going to cover items 38, 40, 41, and 42 at a minimum. I am striking this item from the list. So earthquakes are caused by mainly elastic rebound. So last week we were talking about 3 types of strain. We were talking about brittle strain, we talked about ductile strain, and we mentioned elastic strain, but we said we weren't going to really talk about it much till today. So think of the little door stopper that's on a spring, and how if you pull that back, it's a little rubber thing on a spring so that the door doesn't plow into the wall and bust up the sheetrock. If you pull that little bobber back that's on the spring and let it go, it goes kind of like that. And in other words, because it's elastic and you let it go, it goes back to its original position, but its momentum carries it back past that original position and then back the other way. And it continues to do that back and forth until its energy is released. This is really similar to what's happening in the Earth's crust. We don't think of the crust as being elastic, but it does flex a little bit before it breaks. So when it flexes, it's kind of bent. When it snaps, we have a rupture, and the rupture happens along the focus. So when it snaps, what happens is both sides of the crust where it snapped, they will then fly back to being straight. They were flexed, but now they're going to fly back to being straight. But their momentum carries them past that straight point, and so they do vibrate in much the same way that that door stopper spring does. And this generates seismic waves that emanate from the focus, the point of rupture, or if it's an already existing fault zone, the zone of maximum displacement along that. So you have seismic waves that move in all directions from the focus. Now quickly, the epicenter is probably a term you're more familiar with. The focus is where the seismic waves originate. It's the beginning of the earthquake. The epicenter is simply the spot on the surface of the earth directly above the focus. There's 3 fundamental types of seismic waves. We'll start off talking about body waves, and 2 of our 3 fundamental types belong in this category. We're talking about P waves and S waves. Body waves are generated at the focus. Surface waves are our 3rd type, and they're generated at the epicenter. So we have 2 body waves and then surface waves. That's our 3. So let's look at the body waves. 2 types of body waves, P wave and S wave. P wave is called the P wave because it is primary wave. It's the first one to arrive because it is the fastest wave. It's always the first one to arrive. Its motion, the way that it moves the earth as it passes through the earth is a kind of a compression dilation. This differs from the S wave, which is slower. The S could stand for shear, but also for secondary. S wave is slower than the P. It always arrives second. And another fact that's actually going to be important to us in chapter 17 is that the S wave cannot travel through liquids. P waves can, S waves can't. On the left-hand side of this figure, you see the motion that's typical of a P wave, and we're going to get to see actually this movement running through the earth here in a little bit. And here is the motion of an S wave, more of a crack the whip sort of thing. Now our 3rd type of wave, again, first type is P wave, second type is S wave, 3rd type is surface waves. We group these all together. These are the slowest of all the waves, so they are last to arrive, but also they move the ground more than P wave and S wave, so they are the most damaging. Let's look for a second what the ground does, what the ground actually does in an earthquake. This link, I already have it open, so I'm just going to go over here to our browser. And here is a quake off of Chile, and we're going to fix it to hit the P wave here. Now there's the P wave passing through, and we're fixing to hit the S right here. And so now we're seeing that crack the wick movement, and then we are hitting the first of the surface waves where it looks really chaotic. This is literally ground moving up and down and side to side as the wave passes through all of these sensors. So that's literally what's happening to the ground in a quake. So how do we measure these quakes? Well, it's actually really straightforward. You got a rotating drum and you got a pin, and that pin will draw a line on that rotating drum as long as there's no shaking involved. But if the drum moves up and down or side to side because of ground motion, then the pin is no longer going to draw a straight line. The drum's moving up and down or back and forth, and so the pin will draw squiggles. Measuring the height of those squiggles from the background, so here's several lines of no earthquake happening, and then we have an earthquake happening here. There's the P wave, the S wave, and then the surface waves. Measuring the height of those squiggles gets us the magnitude of the quake. This figure is really just to show you that the S wave always arrives after the P wave, and the farther you go away from the epicenter, farther they travel, then the farther apart they get. The height of these squiggles gives us the magnitude. Now, we used to call this a Richter scale, and it's nothing against Richter. We still like Charles Richter, but the scale has evolved to the point where it doesn't much resemble his original scale. And so we just call it the magnitude. And so notice it ranges from 0 to 10. We've never hit 10 as far as we know. Now, maybe in prehistoric times, but as long as we've been able to measure, we have never hit 10 on the Richter scale. But on the right-hand side of this figure, you notice the equivalent energy released, and they have several different landmark events that you may be aware of. So all of this energy released really almost simultaneously in the form of seismic waves. So earthquakes release more energy instantaneously than any other natural event. Now, there is a second way in which we measure earthquakes. If the magnitude is simply measuring the amount of energy released, the intensity scale is measuring just what that energy does, just what the shaking does to buildings and people. It's more of a practical scale. So what the Mercalli intensity scale measures is how people responded to the shaking, what they thought they felt, and then how did buildings respond? Did they crack a little bit? Did they crumble? Did they completely fall down? How well built was the building? And so there's several things which will affect the Mercalli scale. Here is one example of the Mercalli scale. It's Roman numerals 1 through 12, and you can see that it ranges from not felt except people that are completely sitting still, maybe just about to fall asleep, and all the way down to total damage, waves seen on the ground surface. So after a quake passes, we then see which one of these fits most closely to the damage that we noticed. And we create a Mercalli map. And obviously, you notice that although a quake will only have one magnitude number, it can have, it will have several different Mercalli intensity numbers. This is because Mercalli will vary based on several different factors. One is, obviously, the higher the magnitude, you're likely to have higher Mercalli intensity numbers. If you get a 9.0, there's likely to be a lot of damage, and it's going to be high up there on the scale. But also how close we are to the epicenter. Generally, seismic waves dissipate, their energy attenuates, they lose energy the farther they travel from the epicenter. And so the shaking tends to be less the farther away you go. But that's not always the case. You see on this diagram, you see islands of greater damage surrounded by less damage, and islands of less damage surrounded by greater damage. So there are other things that come into play. Both what the material that the buildings are built on, and how well built the buildings are themselves. It's not unusual for a 6.0 magnitude quake to cause almost total damage in developing nations, but almost no damage in developed nations because of the quality of the construction, how well they are built to withstand the shaking. In part 2 of this slideshow, we're going to look at the effects of the shaking. What are the different things the effects do to the ground and to the things that are built on the ground?